Thanks for joining today. My name is Anthony, and I'll be discussing my work involving capturing timelines of interest and identifying changes with the neural Hawks processes for mental health monitoring. So there's four main questions that this research is aiming to address. Firstly is how can we efficiently select meaningful timelines from social media data for subsequent annotation? And secondly, there are two related questions of how can we model the temporal dynamics in the linguistic posts to identify changes in mood? And related to this is how can we enhance existing sequence-based models to account for the time intervals between posts? Lastly, there's another related question, which is discusses some ongoing work where we are involving capturing interactions between different aspects of mental health over time. So the data sets these works work on are similar to the ones that Talia had discussed. We also use the TalkLife dataset as well as a Reddit dataset, and they contain the same type of labels. These are moments of change in mood over time, but the key difference between these datasets is the temporal granularity. TalkLife generally is much shorter timelines with much more frequent posting behavior, whereas Reddit occurs over a much larger time span. So this brings me to this first piece of published work titled Creation and Evaluation of Timelines for Longitudinal Posts at EACL. And it aims to address the first research question of how can we efficiently select meaningful timelines from social media data for efficient annotation. This addresses the challenge which I mentioned just now, and the goal is to maximize the annotation efficiency for capturing these moments of change. And it's based on the hypothesis that changes in posting behavior appear near frequent changes in mood. So I'll just illustrate very quickly the way in which we generate these timelines. The most straightforward approach for annotating the social media data would be to, for example, annotate the entire user's history. On the screen is the daily frequency of posts of a given user, and time is along the x-axis. However, if we were to annotate all of the posts in a user's history, this would be very infeasible and result in very low proportion of the rare labels we're seeking to annotate. So instead, we are proposing to make use of a change point detection algorithm. We make use of an algorithm known as Bayesian online change point detection. And this involves modeling the frequency of daily posts via a Poisson gamma temporal point process. And this involves identifying posterior distributions of this variable known as the run length. Very briefly, the run length describes the time since the last change point. And by identifying the maximum a posteriori estimates for when the run length is 0, we identify the change points here. And overlaying these change points on the user history, we identify the following change points. And the approach proposes to select timelines centered around these identified changes in time. And by focusing our annotation efforts around these selected timelines, we're able to get more dense annotations around these periods of time. Compared to another common approach for annotating timelines is to randomly select them. However, this can result in very few posts with very few labels or periods in time where there is very uninteresting behavior in the user behavior. We also explore the use of anomaly detection algorithms, which identify periods of anomalously high posting behavior compared to the user's baseline, and use these to also select timelines. So in summary, this approach proposes to annotate only posts within selected timelines rather than the entire user history. And by using change points to do this, we result in a higher proportion of rare labels and thereby reducing annotation cost. For this example user, the posting behavior is quite homogeneous with very few changes. And as a result, no change points are detected and no timelines will be annotated for this user. Additionally, we propose an evaluation framework for annotating the quality of the timelines and also the methods for selecting them based on their proximity to these dense clusters of labels. So on the screen, we have two example timelines with the ground truth labels in purple. And essentially, we want to select timelines which are rich in these rare labels, for example, on the right-hand side compared to the left. And in addition, we want to select them close to these regions. And we identify these as medoids, which are essentially clusters of these labels, which are identified as either being dense in moments of change or sparse, meaning very few labels. And the evaluation framework involves assessing the distance between our methods for selecting timelines to the proximity of these very dense regions. In terms of the results, we found that Bayesian online change point detection performed relatively well for selecting timelines rich in moments of change. And in addition, selecting timelines based on anomaly detection algorithms of high posting frequency led to timelines of high moments of change. So to summarize this piece of work, it involves proposing timeline selection using change point detection algorithms. It proposes an evaluation framework for both the timelines as well as the selection methods. And we found that selecting timelines based on automatically detected change points led to data which was high in the proportion of the rare moments of change in mood. I'll now discuss some other published work which involves predicting these moments of change. We develop a time-aware hierarchical transformer. This was published at ACL Findings and was titled Exciting Mood Changes, a Time-Aware Hierarchical Transformer for Change Detection Modeling. This work is quite similar to Talia's, which we have seen just now, but we propose a different approach for modeling temporal dynamics. And yeah, we address the challenges of modeling temporal dynamics and enhancing existing sequence-based models by explicitly accounting for the time intervals between posts. So standard sequence models such as LSTMs and transformers, although they're very powerful for modeling sequence data, generally they don't account for time by default. So what we are proposing is by modeling the time intervals and the regular posting patterns between posts, we can recover some very important signal in the user's behavior over time. So there's a technical challenge of how can we simultaneously model the linguistic information, the sequence dynamics, as well as the temporal context in the user's posts. So to do this, we propose a time-aware hierarchical transformer, which consists of 4 main components. Firstly, it involves segmenting the user timelines to be provided as input to a linguistic encoder, and these linguistically aware embeddings are passed through a post-dynamics encoder, which models both the sequence behavior as well as the temporal dynamics. Finally, we have a prediction layer for predicting moments of change in mood. So at the bottom is our segmentation of a user timeline, and the posts are then modeled for their linguistic content using BERT, which is fine-tuned end-to-end, along with the rest of the modules in the model. And on top, we involve a post-dynamics encoder, which can consist of either a transformer or LSTM to model the sequence behavior in the linguistic context. These encodings are then passed through another submodule referred to as HEAT, which is based on the Hawkes process, to transform these sequence encodings into time-aware encodings. So much of this work is based on the Hawkes process for modeling temporal dynamics. And briefly, it is a common approach used in statistical modeling for event data, and it is referred to as a self-exciting temporal point process. It's generally used for predicting the probability of events occurring over time, and we do this by modeling what is referred to as the intensity function. It roughly corresponds to the probability of an event occurring at a given point in time. There are 2 main variables to keep in mind in this formula. Firstly is the epsilon over here, which is essentially the excitement factor, which increases the probability of an event occurring due to a recent event occurrence. And secondly, there is the beta term, which involves the time decay, where the probability of future events decreases in the absence of events. So very simply, in red in this diagram, we have events occurring over time. The intensity, which is the probability of an event occurring, rapidly increases due to an event occurrence. And in the absence of events, the probability decreases over time. So the Hawkes process is generally used for modeling event occurrence, but it's not very commonly used for modeling linguistic data, which is what we're proposing in our work. So to do this, we propose a following formula for aggregating the linguistic and sequential information in posts, which are modeled with the hidden states from either a transformer or LSTM, which is denoted by V. And we also found that by emphasizing more recent temporal context from the recent posts, this helps improve the representations learned in the user over time. And by doing this, we similarly account for the time intervals in posts denoted by tau in the formula, and which simultaneously aggregates the linguistic context and the temporal context in the user's timeline. In terms of the results, we have a few different models which we have on the 2 data sets of Reddit and TalkLife, where the model on the top is our best performing model. The notation refers to Hawk's process over recurrence over BERT, which generally summarizes our model. And we found that the recurrence-based models outperform the others. And in all cases, with the transformer-based model, we found that applying the Hawk's process over the base models improves the performance, indicating the effectiveness of modeling time. And very briefly, I'll discuss some ongoing work which involves multi-stream modeling, capturing interactions between different aspects of mental health. So as we know, mental health is a very multifaceted problem, manifesting through multiple streams of psychological data. And this work aims to model the interactions between these different aspects. So there's the technical challenge of how can we model both the self-excitation within streams of data and also the cross-excitation between different psychologically relevant streams. So in this diagram here, we have 3 different streams of psychologically relevant data: personal life events and mental health symptoms. And each different type of event has timestamps associated with them with different levels of temporal granularity. For example, personal life events may be very infrequent, but they could have a very long-term impact on users with much longer time intervals compared to symptoms. And this work builds on the idea that there are some dependencies which exist between these streams, which we're aiming to model. And additionally, each stream can both be a cause and also a result of other streams. So we're looking to model the impact between each of the events within their own streams, but also how they relate to the others. And we're aiming to approach this using a multivariate version of the Hawk's process. There's also the additional challenge of how do we identify these events. And we're proposing to use large language models to get some automated extraction of these 3 linguistically derived events. I'll discuss that work is ongoing, but if you have any questions, I'm happy to answer about them. But to conclude, in this talk, I've described our work on timeline selection for identifying timelines rich in rare labels for mental health monitoring. And also I discussed some work involving the Hawk's process for integrating linguistic data, where we find that integrating the time intervals between posts leads to an increase in performance for detecting rare moments of change in mood. So on the screen are just some of the publications which were discussed today, where these 2 works are based on the Hawk's process, but today I only discussed this one. So if you have any questions, thank you very much, and let me know.
Great timing. So yeah, other questions?
Is the Hawk's process kind of similar to ARIMA, like a time series thing? Because I've never seen it before, but it sounds... No?
Could you remind me about ARIMA?
It's just a time series, just looking at like the dynamics in a time series, and it just sounds similar to me.
It's part of a type of class of models which are temporal point processes, and they are just used for modeling the event occurrence, the probability of event occurrence by modeling the time intervals. So I'll need to look more about ARIMA. I think I've came across it, but it doesn't seem very well explored in natural language processing. So it could be a good area for research. Thanks.
Anthony, great talk. Thank you. Similar question, but how did you evaluate the use of different change point detection algorithms? Did you annotate or something like that?
Yeah, this is a very important question. So the change point detection algorithms generally are unsupervised methods. And this is a very open area of research of how do we evaluate change point detection algorithms. Generally, it would involve annotating some existing data and then assessing the proximity of those change points to ground truth change points. However, for this data set, we didn't have the annotation resources to annotate exact change points in this. And however, we have some existing timelines which were randomly selected, and by looking at the proximity of those to the change points, we had a rough idea of how well they were able to capture those changes. But in the literature, it's not a very common practice for assessing the change points, as it's an unsupervised method.
Thanks.
We have a question over there, if there's
There
time.
was also, I think there was also an online question. How do we do the online questions? Okay, can you unmute yourself while
Yeah,
yes.
yeah, can you hear me?
Yes.
Yes.
Yes, thank you so much. I got very similar questions. So also when you refer to the time series modeling, so I was curious about like some models like the LSTM, they require some regular time interval across different multi-variable. So in your event series, are they also the regular interval or also in regular things?
Thank you for your question. So the work involving the Hawkes process, which transforms those LSTM representations, these we don't assume that there are equal spacing between the events. Generally, LSTMs would assume that there's no the spacing between the events is equidistant. However, we instead getting the representations learned from the LSTM, we then transform them by incorporating the time intervals. So it's quite generalizable to different types of sequence-based models, which generally don't account for the time intervals explicitly.
I see, yes. Thank you.
Thanks.
Pat?
Yeah, just wondering how you're assessing, I missed it, I'm sure you said mood change. Was it self-assessment?
We have, sorry, could you explain again?
Moments of change, basically how we assess the moments of change.
In this model, we just have a data set which is already annotated with moments of change, and it's just a simple classification task. But in terms of so we're just seeing whether the predicted labels match the ground truth labels.
So the ground truth was like psychiatrists rating.
It was actually university educated students, but we also had some expert psychologists who helped guide the
we had annotation guidelines on how a change given a timeline. So one sort of difference in this annotation was that it wasn't around like having a Likert scale, for example. It was sort of judging, looking at sort of posts and sort of basically saying whether there's been a change from point to the next, from one post to the next. And so most of them were no changes, but then you had switches. Several posts long.
So it wasn't categorized by psychological state or something, it was just mood change.
Yes.
So, thank you.
But we're doing some annotation with psychologists at the moment. Well, they've already been doing some also in the context of the CL Psych shared task, which is